Okay, students. So what I'm looking at here is a what you call it is a we're looking at a word problem, and the word problem for the independent practice says a 120-pound weight is placed on a lever 5 feet from the fulcrum. How far from the fulcrum should an 80-pound weight be placed to balance the lever? I told you this involves physics. This is a big one. This is a one. Levers are a big thing in physics. Now you may say, well, what's a lever? What does it look like? I don't know what a lever looks like, in my mind. Well, you do know what a lever looks like. Your lever looks like that. A seesaw. All of us have been on a playground and been on a seesaw. Now, if you notice something about a seesaw, it works best. There's a little mouse here. It's a little hard to see. There's a mouse. Seesaw works best when two people are close in weight. Two kids on a seesaw are great because you're bouncing up and down. The both of you going up and down the whole time. It's easy to push the other one off. What happens is I always remember like maybe going with my dad or my grandfather to the playground. And I used to be like, I want to go on the seesaw. And I would sit here. And my grandfather, who was a big man, he used to sit over there. And we'd go all the way down. And I'd be all the way up here. And I couldn't go down. He would just sit there and laugh because he was a joker like that. And I was stuck up there. Now, this is a lever. Now, the point on a seesaw where everything pivots, the little hinge, if you want to think about it, is that right there. That's the fulcrum. Now, the trick with a fulcrum and a lever and the idea of leverage, okay, some of us maybe know what leverage is using some sort of lever to gain a mechanical advantage, a weighted advantage. Now, the question is here, it doesn't look like this would ever work. How could you ever balance the weight between the two of these? Well, the idea is I could make a lever, we could make a seesaw, where the mouse would be able to hold up the weight of the elephant. It sounds crazy, but it's true. If I just have to make this longer, and after a certain amount, it's a certain distance away, we can balance it. So if the mouse is all the way on the edge, all the way out here, I don't know how much, it's probably going to be a lot of distance. But if I made a seesaw like that, I could balance the two of them. So basically the idea is the distance you are from the fulcrum and your weight are inversely proportional or inversely variant. So that means if I weigh less, as my weight decreases, I have to keep this balanced. I have to go further and further out this way. As my weight increases, to keep it balanced, I want to come closer and closer to the fulcrum. So if you do it the right way, if you have a lot of length over here and a little bit of length over here, you're going to be able to have the mouse sit on the end of the seesaw like right here where he's down. So you could have a situation, I'm going to draw it, kind of keep it extreme. So we keep the fulcrum, right? And we keep let's say, the elephant. I'm terrible at drawing elephants. We have the elephant over here. It's not a bad elephant, right? But if you have the mouse all the way over here, I'm also bad at drawing mice. If you have that something that extreme, that far away from the fulcrum, you could do that. That's totally possible. It's a law of physics. So, how do we do it with this one? So think of a seesaw. Fulcrum, lever. Same thing, I'm going to draw a seesaw. Now, instinctually, it says 120-pound weight. So this is like the elephant side. The 120 pound, the bigger weight, is 5 feet from the fulcrum. So 5 feet in that direction. Now, they want to know how far an 80-pound weight needs to be from the fulcrum. Well, we know right away it should be bigger. So we're saying as this weight goes down, it needs to be bigger here. This needs to increase. So, my question is, what is my x and my y? Well, I'm searching for this. And if you remember, inverse variation tells us this, y equals k over x. So my x values are going to be my pounds. Okay? LBS is how you say pounds. And my y value is going to be the distance. So how far away does that block have to be over there? Okay, so let's figure it out. Well, I know one set of information. I have one x and I have one y. That's over here. My x is this, my y is that. So let's find k. If we remember from the last one, k equals x times y. Well, I look at 120 times 5. Okay, so what is 120 times 5? $120 times 5 is 600 in my calculator. So k is just 600. Now, I can put it back in to this wonderful formula we've created. Y equals k is 600 over x. So you give me a weight, and I will tell you how far it has to be to balance this system out. How far is this balance? Well, my x here is my weight. Y equals 600, and the weight that we're looking for on this side is 80. So how far away does our other box have to be? So I can take 600 and divide it by 80, I get 7.5. So it's 7.5 feet away. So it's a bit more, about 1.5 times away. That's very interesting, because the weights are 1.5 times different. So very interesting. So if you're curious, let's try and do this problem real quick. Okay, because I'm kind of inspired by this problem. Do it quick. How much does an elephant weigh? I'm going to go on my computer and check it out. www.google average weight of elephant. Oh my God, an average weight of an elephant is 1,300 pounds. And let's say he was 10 feet from the end of our fulcrum. A mouse, the average weight of a mouse. Weight of a mouse. Probably doesn't even weigh a pound. Oh my God. Weighs about an ounce. How many ounces are in a pound? How many ounces in a pound? There's 16. Okay. So he weighs 1/16 of a pound. 1/16 of a pound. Let's put it into decimals, make it a little bit easier on ourselves. 1 divided by 16, 0.0625. He weighs 0.0625 of a pound. Man, he's small. But we know this here. So, first we got to look at this. What's our K? Well, K is Y, which is the distance, which is 10 times 1,300. Okay? Well, 10 times 1,300, you do this, and you put in your calculator, you get 13,000. Now, 13,000 is my K. So my next question is, if he's 10 feet from the end, 1,300 pounds, how much far away does the mouse have to be to balance his fulcrum? So I have y equals 13,000 over his weight, 0.0625. It's going to be a huge number, okay? I didn't say it would be easy to do this. I'm just saying you can do it. So what I'm going to do here is 13,000 divided by 0.0625. A little disappointing that it's going to be so big, but you could do this if you had the other side of the seesaw be 208,000 feet long. Pretty long. It's miles. Okay? So just an interesting idea. Could you do that? Yes. It'd have to be ridiculously long, but it's possible. Okay? According to laws of physics. Okay, guys. I hope you have a great day, and I will talk to you tomorrow. Stay safe.